In this video we can look at the results of solving the Schrödinger equation for the hydrogen atom. Schrödinger equation is the fundamental equation in quantum mechanics. It describes the behavior of particles in the smallest level, and it describes the properties of electron in the hydrogen model. And this equation is based on classical wave equation. In order to solve Schrödinger equation, he used quantized energy. That is, the electron in the hydrogen atom can have only fixed values. Quantized, it means that the electron can possess only certain discrete energy values. He used the Greek letter psi for representing the wave function. For tracking the waves, he used the three quantum numbers: n, principal quantum number; l, azimuthal quantum number; m, magnetic quantum number. And n can be any integer numbers 1, 2, 3 and so on, and l start with 0 and ends up with n minus 1, and m sub l start at negative l, counts up some negative integers, passes 0 and ends up with positive l. This describes a particular wave function. When we look what is the wave function tells us, we take the wave function psi, it's a mathematical wave function, and square, it says something that the probability of finding the electron in somewhere. What this mathematical function look like? We can see it in three different types of plots. First one is a radial plot. Just imagine here is a nucleus, a proton, and electron are located far away from the proton, and draw a line from the center of the nucleus to the electron. This line is called radial distance r. Draw a plot here, x axis and y axis. We can take the probability on this axis, y axis, that is psi square, and we can take radial distance r at the x axis. This plot tells the probability of finding the electron some distance from the nucleus. Second one is the dot plot. In this plot, the density is higher in the middle and low as we go away from it. Lot of dots in one area, that is the middle, have the higher probability density. Further and further away, the probability falls off. Third one is the radial probability distribution plot. For hydrogen wave function, we can choose different values of the quantum numbers and can see what different wave function look like. So here first we choose the quantum number for n is the smallest as possible, that is n equal to 1, and l will be 0 and m sub l also will be 0. We can write it psi 1 0 0. If l equal to 0, the symbol is s, and also we can write it psi 1s. According to German physicist Max Born, the square of the wave function, that is psi square, at a point gives the probability density of the electron at that point. This plot is radial plot. Right here, this point is 0. It indicates the top of the nucleus. This is psi 1s orbital wave function. For 1s orbital, the probability density is maximum at the nucleus, and it decreases sharply as we move away from it. And this plot is called dot plot. The probability density of electron is maximum at the middle, and further and further away the electron density decreases. The next kind of plot we can look at called radial probability distribution plot. So in radial probability distribution plot the total probability of electron being in a spherical layer. Let's imagine we take a whole atom and we can break up into little spherical cells. It seems like the skins on an onion. And what is the probability of inside the circle? What is the probability of electron some distance or from the nucleus? The way we calculate it, we take the size square and multiply it by the volume of the shell. Right here in the middle, the volume is 0. So multiply the probability times 0. So further and further away from the nucleus, the volume of the shell increases and the radius goes biggest. A typical plot, it goes up as a peak and comes down back. For example, falling off apples from the tree. And count the number of apples in the given rings. Right here, the trunk of the tree, there is no apple fall, so this is here 0. In the first ring, there are several apples but not many because the ring is small. Further and further away, the ring going bigger, so the number of apples in each ring would be many. So the plot reaches a peak. Peak tells the most probability of finding the apples, and this peak is the most probability of finding the electron. Another kind of plot is contour plot. Contour plot shows the shapes of the orbitals. Look at the dot plot. Draw a surface on it. Close like 98 to 99% probability. Probability of electron anywhere of the surface would be same. So that contour plot look like a ball, a sphere. This is 1s orbital. Nucleus is at the middle. Further and further away, the probability falls down. Next, we can see psi 2s wave function. For psi 2s wave function, here we have 3 types of plot. The first one is the radial plot, then another one is contour plot, and the next one is the radial probability distribution plot. When quantum number n equal to 2, then L will be 0 and M also will be 0. Called psi 2, 0, 0 wave function, also known as psi 2s wave function. This is 2s orbital. Here the radial probability falls off and goes to 0 right here. Then it climbs up back again and the probability again falls down further and further away from the nucleus. And the points where goes absolutely to 0 is a node, also called radial node. Everywhere the distance from the nucleus, the probability of finding the electron is 0. Here the dots is very concentrated at the nucleus, and again this is 0 probability of finding the electron, that is node. And this node seems like a ring or like a shell. Here we can't see any probability, and further the probability increases and finally gets small again. The overall shape is a ball, a spherical shape. And at this side here we have the radial probability distribution plot. Again it's 0 at the nucleus because the shell at the nucleus has 0 volume, and if we multiply by psi square we get nothing. Then it comes high a little bit and comes down, and here is a node. Again it climbs up back, and here the volume is big. This peak is the most probable distance from the nucleus. Here the probability is far away from the nucleus than the 1s orbital because this is 2s orbital. The next one is the psi 3s orbital wave functions. The radial plots come down and here is a node. Comes back and here is another node. And this radial plot has 2 nodes. Here the nodes also shown on the contour plot. At the right side we have the radial probability distribution plot. For n equal to 3 we have 3 modes. It has 2 nodes, and this area is the most probable distance from the nucleus, and the overall shape is seems like a ball. Here the important thing is nodes. The nodes are where the region has zero probability, and we know the hydrogen atom, it has one electron. Here the hydrogen atom's electron described by psi 3s wave function, and the one electron of hydrogen really close to the nucleus. It is 2 angstrom here from the nucleus, and here it is 7 angstrom from the nucleus. Here there is zero probability of electron, and find here there is good probability of finding the electron. How's the electron get here from here without ever passing to this point right here, where the points has zero probability density, and how it's moving from this side to another? Well, here is the Heisenberg uncertainty principle. It says we can't certainty tell where's the electron's probable location and how fast it's moving. In quantum mechanics, we can't get the right answer for this. All these are S orbital wave function, 1s, 2s and 3s. S orbitals looks like a ball. When the quantum number n increases, the size of the balls also increases. This plots also similar kind of plots. The above here is dot plot. This dot plot have outside sketch like a contour plot, and below right here we have electron distribution plot. This plot is distance from nucleus versus electron distribution. Here the electron distribution is volume of one of those shells times size square. The nodes also indicated here clearly. Here the psi 1s orbital wave function have no nodes, and the psi 2s orbital have only one node, and the psi 3s orbital have two nodes.